Hello. This is the tangent problem that we are addressing in section 2.1 of the James Stewart calculus text. And I thought that we should review how to simplify the difference quotient, because as we embark on our study of limits, we're going to end the chapter with the definition of the derivative, the limit definition of the derivative. So one of the main ideas in calculus all along, especially in first semester calculus, is the tangent problem, how to calculate the slope of the tangent line to a curve, and also how to find the equation of a tangent line to the curve. So what is a tangent line? Usually from an elementary geometry course in high school, or maybe a beginning analytical geometry course or pre-calculus course, you studied some circles and you knew that the tangent line to a circle only touched the circle at one point. So the same idea applies to a tangent line to a curve. We want to find the, for a particular point on a curve, we want to be able to find a tangent line that actually describes the behavior of the graph at that point. Like, is the function decreasing at that point? Is the function increasing at that point? We're going to discover in our applications of derivatives and slope that we've got some great applications that we can use, like marginal cost, marginal revenue, or instantaneous speed of an object traveling in time. So we want to first just start from what we know from our algebra, and just how to calculate the slope between 2 points, and also how to approximate that or set that up in an abstract way, because we're going to be applying limits to that as we define the derivative of a function. So what you see here, let y equal to f of x be a function whose curve lies in the xy plane, then the slope of the secant line, and the slope of a secant line is just going to connect 2 points on the graph of a function. So if I just back up here, if I took this point here and I took this point here, I could connect the dots and I could have a line there. And of course, if I have 2 points on my function, I can calculate a slope. And if we remember what slope means, that is the change in y over the change in x. That's how we define the incline of that line. If the slope is negative, then it is a decreasing line, so you would go from the upper right to upper left to the lower right. That would be a negative slope. And from lower left to upper right, that would be a positive slope. And slope meaning incline, right? If we had a flat line, we would have 0 slope. And if we had a vertical line, we would have an undefined slope. Now we use this delta y over delta x notation a lot within calculus, and that really does mean the change in y over the change in x. And remember, if y is equal to a function, y equal to f of x, and if we had 2 points, a, f of a, that would be on our graph, and b, f of b, that would also be on our graph, because the output y would be the function output at that value a. Then we do see f of b minus f of a over b minus a is our change in y over change in x. And you might also make that connection with the y2 minus y1 over x2 minus x1. So now we extend it to other notations that you will see in various calculus textbooks, where we introduce this arbitrary distance h. Okay, so notice here that between a and a plus h, we have a distance h, right? But if we were trying to calculate the slope of the tangent line, which is what you see in pink up on the curve, we're going to want to first try to calculate the slope of a secant line to a point that's very close to that point A, maybe a small distance h away from A. So if we just go a small distance h away from A, we get to A plus h. And if we calculate the output on our curve, f of x, then our input would be a plus h, and our output would be f of a plus h. And if we wanted to calculate our slope here, we would have this y2 minus y1. And remember, this is going to be a plus h minus a, and so you would get that f of a plus h minus f of a over h, because the a's would cancel each other out. A minus a is equal to 0. Good. You also might see in other textbooks where we just have this arbitrary value a, and we have another arbitrary point x, and we would say that the slope here would be f of x minus f of a over x minus a. Good. And in this case, we would be wanting to look at values of x as x approaches or gets closer to a. Right? And here we're going to say, look at values of a plus h as h approaches 0, because that will make a plus h get closer to a. And of course, as we get closer and closer to the point A, our slope of our tangent line can be more accurately approximated. So I thought we should practice just simplifying using our knowledge of algebra and simplification of algebraic expressions, how to simplify the difference quotient, because that will be very helpful after we study limits and calculating the derivative of our function, and our derivative will be defined as our instant rate of change. So let's start with a very simple one, and what we basically want to do is build or engineer this f of a plus h minus f of a over h, and it's the same similar process over and over. It's just that some of the algebraic functions get a bit more complicated as we go along. So let's build our difference quotient, and remember the difference quotient is f of a plus h minus f of a over h, and that does define the slope of the secant line. Connecting a f of a and a plus h f of a plus h. And since they're arbitrary points, then we can actually apply that formula for slope to any point A on our graph. All right, so we have f of x equal to 3x minus 8. What is f of a plus h? Well, wherever x appears, we're going to substitute a plus h. So we're going to put in here a plus h, because that's what we have as our input value, and we can clear our parentheses to get 3a plus 3h minus 8. Now we want to do baby steps and build our difference quotient, f of a plus h minus f of a, and in this case we want to be careful, since we have two terms, to subtract the entire function. So this is going to be, we have our a plus h before, and that's going to be 3a plus 3h minus 8, and now we want to take away, and our function is 3x, or 3a minus 8. Good. Now we want to be able to clear our parentheses and collect like terms. We get 3a plus 3h minus 8. We get minus 3a, and minus turns into a plus. We see that 3a minus 3a cancels out, and minus 8 plus 8 cancels out, and we are left with 3h. Our next step is in our final step we do f of a plus h minus f of a, and now we want to divide that entirely by h. So we are going to divide this side by h. We can now cancel our h, and we end up with 3. And that is the value of our difference quotient. As we get more complicated, we're going to end up with a's and h's, potentially. Good. So here, instead of using a, now I'm going to actually just use t. So I'm going to calculate, or g of t plus h minus g of t over h. Good. And we have 1 over the square root of t. So baby steps. What is g of t plus h? G of t plus h is whatever I have as my input goes under the radical. And now what is g of t plus h minus g of t? We just have one term each, so we can just write 1 over the square root of t plus h minus 1 over the square root of t. Next up, we want to divide by h. On both sides. And we'll have 1 over the square root of t plus h minus 1 over the square root of t, and we are all dividing that by h. I don't know about you, but I know I don't like complex fractions. I don't like fractions that have denominators in the numerator and denominators in the denominator. So I'm going to first get rid of my denominators in the numerator by multiplying on top and bottom of my fraction by the lowest common denominator. So I tend to, and I see here that square root of t plus h times the square root of t. If I were to multiply that on the top, it would get rid of my denominators. But if I'm going to not change the value of my fraction, I also need to divide by t plus h times the square root of t. And now I'm going to distribute in there, and I end up with, in the first distribution, the square root of t plus h's cancel, and I end up with square root of t. In the second distribution, the square root of t's cancel, and I just end up with the square root of t plus h. And in the denominator, since we multiply the numerators and multiply the denominators together, I just get h times the square root of t plus h times the square root of t. All right, our goal here in simplifying the difference quotient is really to get rid of, or to cancel out, the h. So I want to manipulate the expression that I have here so that I can actually remove the h. That's our goal. And that will become clear later on when we're calculating limits, why that is the case. Because really h is going to be approaching 0, and we don't want to be dividing by 0, and we want to be able to remove that. So with that difference of radicals, usually to get rid of radicals that are subtracted or added together, we want to multiply what's known as the conjugate. And so we're really employing that rule of a minus b times a plus b would give me an a squared minus b squared. And if I square my square root, the radical goes away. So that's what I'm going to try to do here. I'm going to multiply by the square root of t plus the square root of t plus h over the square root of t plus the square root of t plus h. Okay, so when I do that, I'm going to end up with, in the numerator, I'm going to get square root of t squared, which is t, and I'm going to get the square root minus the square root of t plus h squared, which is just t plus h. That is my a squared minus b squared. And in the denominator, I still have, but if I were to, if I were to multiply through or to distribute, I would end up with h times t times the square root of t plus h. Or actually, I don't need to. I can just go ahead and not distribute and keep that h just where it is, and just for the time being have h times the square root of t plus h times t times the square root of t plus the square root of t plus h. So far, so good. Now I'm going to clear the parentheses of my numerator, and I get t minus h, and so that's going to give me minus h over h times the square root of t plus h times the square root of t times the square root of t plus the square root of t plus h. I have multiplication in the denominator, and this is multiplication in the numerator. I am able to cancel my h's, and so I end up with, at the moment, minus 1 over square root of t plus h times the square root of t times the square root of t times the square root of t plus h. Now I'm going to just distribute the denominator just to see if I can clean some of these things up. And I'm going to get minus 1 over root t times root t is t. And I'll have t over t plus h plus, and then I have root t plus 1 times, or plus h times root t plus h is going to give me t plus h. And then I'll have my times root t. And you can leave it like that as simplification of the difference quotient in calculus. You don't necessarily need to rationalize your denominators, but in terms of simplifying the difference quotient, you will want to eliminate your h in the denominator as a product. Because in this case, if we were to substitute the value of 0 as h goes to 0 here, we would end up with minus 1 over t root t plus t root t, and we would get minus 1 over t times root t, or minus 1 over 2t to the 3/2. And for those of you who already know how to calculate the derivative using shortened derivative rules, you know that that would be the derivative of 1 over root t, just to make that connection. Finally, I'll just do one more just to drive home the simplification of the difference quotient. Let's say we had f of x equal to x squared plus 1. Calculate, find the difference quotient f of x plus h minus f of x over h. Good. So we already have the value of f of x. So what is the value of f of x plus h? The value of f of x plus h is going to be x plus h squared plus 1. And please do not distribute the exponent. That is going to be x plus h times x plus h plus 1. And that's going to give us x squared plus 2xh plus h squared plus 1. Next, we build our difference quotient. by first subtracting f of x, and since f of x is two terms, we want to make sure that we subtract the entire function, and this is going to give us x squared plus 2xh plus h squared plus 1, take away x squared plus 1. Let's clear our parentheses, and we get x squared plus 2xh plus h squared plus 1, take away x squared, and take away 1. Now at this stage, since our goal is to factor out our h and cancel it from the numerator and denominator in the very next step, you know that you have made correct calculations if you get to this stage and you are able to cancel all of the terms that do not contain h. And we see that we're allowed to do that because we have x squared minus x squared, and that's 0, and we have 1 minus 1, and that's also 0. So we're ending with f of x plus h minus f of x simplifies to 2xh plus h squared. So our next step is to divide by h. And then we'll divide both sides by h. And if we want to cancel our h, and that's our goal, we're going to factor out the h from the numerator expression. And so we'll be able to cancel common factors in the numerator and denominator. And finally, our difference quotient here will be 2x plus h. And for those of you who remember how or know how to calculate the derivative of x squared plus 1, the derivative of x squared plus 1, you will find out quickly, is going to be 2x. And if I were to let h go to 0, then this is going to go to 2x plus 0 equal to 2x, and that will be our derivative. Okay, so that does it for simplifying the difference quotient for section 2.